So today we are going to talk about capacitors and capacitance. And we'll start off by describing what physically a capacitor is, much like we did with inductors the other day. Oh, it looks like it's working or about to work. Wonderful. Thank you, Ashley. All right. Excuse me. So a capacitor I could draw these lines in parallel. Is really kind of a sandwich structure like so. So we have two metal plates. That is not what I meant to do. And they are separated by some distance d. Okay. And we can say that the plates have a width W and a length like so L. And we're obviously going to have another terminal down here. Capacitor is another example of a two-terminal device. And it is very likely that the region between the plates is filled with what we're going to call a dielectric material. So that we have a sandwich of our top plate, our dielectric, and then down here is our bottom plate. Okay. So what a capacitor does is it stores energy in the form of an electric field that's sustained between the two plates, okay? And it does that by accumulating charge on the plates. So if we consider the top plate to be the positive polarity terminal of the device, and the negative plate, or excuse me, the bottom plate to be the negative polarity terminal of the device, effectively what happens is for every positive charge that gets put on the top plate, it attracts a negative charge to be stored on the bottom plate, so that the amount of charge stored on the top is matched by the amount of charge stored on the bottom plate at all times, okay? This understanding is key to realizing how current flows through one of these devices, because it doesn't actually flow through it at all, okay? These are two metal plates that are physically separated from each other with a medium in between whose job it is to keep current from flowing, okay? So we observe current flowing by moving charge onto one plate and then letting it go. Because when we move charge onto the plate, we see current flowing into the positive polarity terminal. And when we let charge go away from the top plate, we have current flowing out of the positive polarity terminal. Similarly, let's say we moved a proton to the top plate, we're moving an electron onto the bottom plate. They're moving in opposite directions, but positive charge, or excuse me, positive current is defined in the direction of positive charge flow. So if a proton is moving down and an electron is moving up, we see a net current flowing down through the device, okay? That's what's called a displacement current, and the observance of this displacement current is actually what started Albert Einstein thinking about the concept of relativity. Okay? So kind of a kind of a big deal. For our intents and purposes, though, we don't have to think about things that strictly. That displacement current effectively acts in the same way as a normal current would. So to us, it's just another two-terminal device that has a particular relationship, okay? So these plates are used to separate charge. So we can say that charge Q is equal to capacitance C multiplied by voltage V that keeps the charge in place, okay? So that capacitance is the ratio of charge over voltage, and therefore has units of coulombs per volt, which is the same as an amp second per volt, or 1 farad with the symbol F. Capacitance, the ability to store charge for an applied voltage, is very geometrically dependent, okay? So for a parallel plate capacitor, like the one I've drawn, C is equal to epsilon, which is the permittivity of the dielectric material, times W, the width of the plate, times L, the length of the plate, divided by D, the distance between the plates. The closer we can get those two plates together, the more capacitance we observe. The larger the plates are, the more capacitance we observe, okay? The permittivity is a material property of the dielectric, okay? So vacuum has a permittivity of 8. Oh, let me write this down, okay? Epsilon naught is what's known as the permittivity of free space. And this is 8.854 times 10 to the negative 12 farads per centimeter. All materials are measured with that permittivity as a reference, okay? So air has a permittivity of like 1.001 times epsilon naught. So air behaves almost exactly the same as a vacuum would, all right? Silicon, which is the dielectric material used in a lot of capacitors, has a relative permittivity of 11.6. So it's almost 12 times as good at storing charge as a vacuum. One of the highest relative permittivity materials that exists is actually deionized water. It has a permittivity of 81. So it's used in very, very large scale capacitors in like nuclear power plants and all that kind of good stuff to store lots and lots of energy in a confined space, okay? Let's bring things back around to, sorry, my wife is texting me that apparently somebody is a doo-doo head. So let's bring things back around to circuit analysis stuff, all right? Circuit characteristics of our capacitors. So we're going to have two different schematic symbols, and they mean different things, or at least they're supposed to. Okay. So the first symbol that we're going to look at is this guy right here. Okay. And it represents physically what a capacitor is. Two parallel plates separated by some small gap. all right? This element exhibits some capacitance C, and since it obeys the passive sign convention, we should expect that a voltage drop, VC of T, will have a corresponding current, IC of T, where the current flows into the positive polarity terminal. Means that this guy is absorbing power, and if the current were flowing into the negative polarity terminal, this guy would be supplying power. Since this is an energy storage element, it is actually capable of supplying power. This is the symbol for a generic capacitor. There's a second symbol that is often used that is very similar, where one of the plates of the capacitor is shown as a curved line. This is what's known as an electrolytic or polarized capacitor. And so for one of these electrolytic capacitors, if you install it in a circuit the wrong direction, meaning if you apply a positive voltage to the negative polarity terminal, it actually causes the device to fail. It'll literally pop. So if any of you guys have ever opened up an electronic device or anything like that, you might see like these kind of large cylinders. And then on the top, there's usually a little metal plate, and it might have what looks like a plus sign on it or something like that. And if your device just all of a sudden stopped working, you might see that that flat plate is now actually kind of rounded over. That is an electrolytic capacitor, which is burst and is no longer working correctly. Actually, fairly common to happen. Yes, sir. Polarized. Yeah, polarized, because it can only be put into a circuit with a specific polarity for it to work correctly. Okay. In this class, we're only going to be dealing with generic capacitors. Okay. So the polarity will not matter at all. But some of you may be doing projects and all that kind of stuff for other classes sooner rather than later, where you might have to look at a schematic and you see this guy, and I wanted to at least let you know what the heck it was. All right. And it also, some textbooks, not that it particularly matters because we don't really use one in this class, but some textbooks just use the electrolytic capacitor model for everything for whatever reason. And that's technically not correct, but really shouldn't matter with regards to circuit analysis. All right. So let's talk about our current voltage relationships here, okay? Current I of T through a capacitor, by definition, is just the derivative of the charge stored on the capacitor with respect to time. This is literally the relationship for current that we've been using since the second day of class, all right? But we know now that for a capacitor, charge is related to both the quantity capacitance and voltage. And so this will become C dV by dt. This is our first equation. It should look similar to what we saw with inductors the other day, right? Just as a quick aside, for an inductor, we observed that the voltage drop over an inductor was L di by dt. These two equations are identical if we swap L and C and we swap I and V. That will actually be true for every single one of our capacitor relationships that we're going to deal with today. These two elements are known as electrical duals. They fulfill the same role in a circuit, temporary energy storage, but one does it in response to a changing voltage, the capacitor, and the other does its job in response to a changing current, which is the inductor. They behave identically. All of the relationships are literally of the exact same form, and you can get them simply by swapping L and C and I and V. All right. So for the derivative-based relationship for an inductor, we were able to come up with two observations. And we'll get two observations for the derivative-based relationships for our capacitor as well. Okay. So what was observation number one with inductors? Anybody remember? Or can find it in their notes or anything? Bradley.
In a DC circuit, a short circuit.
All right, so the first observation we made was in a DC circuit, an inductor behaves like a short circuit. Based on this relationship, how do you think a capacitor behaves? An open circuit, absolutely right. So if the voltage is constant or a DC value, the derivative of the voltage is zero, which tells us that the current has to be zero. And then whenever we have no current, that is open circuit-like behavior. So we can say in a DC circuit, capacitors behave like open circuits. What was our second observation? So in an inductor, the current cannot change abruptly. So what do you think happens in capacitors? The voltage can't change abruptly. Exactly right. So we can take equation one and we can mathematically rearrange it and find a second equation that says the capacitor voltage VC of t is equal to 1 over c times the integral from negative infinity to t of IC of x dx, which is the same as 1 over c integral from negative, excuse me, from t naught, not negative t naught, to t IC of x dx plus VC at t naught. Again, literally the exact same equation. Shaw. Oh, I'm sorry, yes. That's how similar these things are. I can't even write the names down correctly. Voltage drop across a capacitor. Thank you, Shaw. Cannot change abruptly. Let's call this guy number 2. And again, this equation is literally nothing more than the current equation for an inductor, except that we've swapped all of our L's for C's and changed the position of all of our I's and V's. Okay. So for power, we'll still have capacitor current times capacitor voltage. This is now going to be C, V, dV by dt. And lastly, sorry, these shouldn't have these over here. 3 energy is going to be 1/2 C V squared. Those are our 4 relationships. They are, again, the electrical dual of the inductor relationships that we spent time actually bothering to derive on Wednesday. Right? I don't feel the need to really do all of the derivation again because it's literally what we did 1 class meeting ago. Right? So we can wrap things up by simply discussing how capacitors combine. So let's take multiple capacitors in series. We have capacitor C1 in series with a capacitance C2 in series with a capacitance C sub n. Let's say that we have a total voltage drop V of t across this series combination of capacitors. And because they are all in series, they carry the same current I of t. We could say that the voltage drop over capacitor 1 will be V1 of t. Voltage drop over capacitor 2 will be V2 of t, all the way out to the voltage drop over capacitor n, which will be Vn of t. If we apply Kirchhoff's voltage law, we could see that V of t is just V1 plus V2 all the way out to Vn. And substituting in our integral-based relationship, which will put everything in terms of the current that's flowing through all of them, we'll have 1 over C1 integral from -infinity to t of I of x dx plus 1 over C2 integral from -infinity to t of I of x dx plus 1 over C sub n integral from -infinity to t I of x dx, or 1 over C1 plus 1 over C2 plus 1 over Cn integral from -infinity to t I of x dx. And therefore we can see that capacitors in series combine like resistors in parallel. And it should stand to reason then that capacitors in parallel combine like resistors in series. So even these combination relationships are the same but inversely related, right? So if what we covered regarding inductors made sense on Wednesday, everything here regarding capacitors should be equally as easy to follow because it's literally the same relationships, except that the I's and B's are switched. All I have for today. Unless anybody has any questions or anything. Bradley.
energy, doesn't seem to be
Yeah. Yep, absolutely. Connor. Yes, so that's a fantastic question. So if we say that inductors combine like resistors, then capacitors combine like conductances. That's absolutely correct. But we never fully fleshed out how to do conductance combination because I told you guys, make them all resistors and then treat them as resistors. But you're 100% correct, yeah. Any other questions? It absolutely will be. But so we see here. All right, so when we had resistors, let's just do this as a quick aside here. No, not a problem at all. So when we learned our resistor combination techniques, we had for resistors in parallel, let's call this guy R1, R2, all the way out, R sub n, right? This is our current flowing in, let's call it I. Let's not worry about a time dependence here. Won't particularly matter, but let's just call it I to make things easier. Let's call the voltage drop over all of these guys V. The current flowing through resistor R1, let's call it I1. Current flowing through R2, let's call it I2. Current flowing through Rn, well, IN. So if we apply Kirchhoff's current law here, what we'll find is that I is equal to I1 plus I2 plus I sub n, right? Which means V over R1 plus V over R2 plus V over Rn, or V multiplied by 1 over R1 plus 1 over R2 plus 1 over Rn, right? So V over Req, where Req was this guy 1 over R1 plus 1 over R2 all the way out to 1 over R sub n, this whole thing to the negative first power. Right? So it's literally the same relationship, except that we have that pesky integral sign thrown in there too. Yes, it's still 1 over C1, and so the inverse of 1 over C1 plus 1 over C2 plus 1 over C3, et cetera, et cetera, et cetera. Yeah. So literally directly like how resistors combine in parallel. Anything else? All right. I will be meandering around the room helping out with your in-class assignments if you feel the need for it.